Hi everyone, here we're going to go over the k nearest neighbors algorithm. So this is a supervised learning algorithm, so it needs labeled data, but it can be used where the target variable is for classification. It's a nominal or categorical variable, or it's a numeric variable. That is, we kind of use it as regression. So both of those are possible. Note that K and N, for short, K nearest neighbors, assumes that values near each other are similar and it groups items together based on distance. The K refers to the number of neighbors data points that we will use to classify a new unseen data point. So let's go over this a little bit. So the idea is that the main calculation is really how distant points are from each other. That is how distant the data instances are from each other's. Now there are different ways to calculate distances, so it gets a little bit complex, but you can see this link over here for more details, and you can explore this a little bit as you see appropriate. Here we're just going to take an overview. So I like this diagram here because it kind of gives an idea of how it's working. So say you want to classify the gray point into one of the classes of the data, like lime green, green, or orange. And you have existing ones plotted on this two-dimensional graph. We have a x variable, and let's call this a y variable. And we have some data points, and these over here on the high axis and low y are associated with orange. Here it's more medium to high x, and high y associated with green, and here medium y associated with low x. So, and we have a new item. We don't know what this is, but is it part of, which group is it part of? So what the K and N does is actually calculate a distance between this point and all the other points. Now, but actually before it does that, when you build the algorithm, it has to calculate a distance between all the points. So it needs to know how distant all the points are from each other. So this distance calculation is essentially what the K and N does. So even before we identify how all the points are near this new point, it needs to identify what's the distance between each of the points. And then once it does that, then we can find the neighbors. So you can make the calculation and just colored here. So the new point that is introduced to the algorithm, it says, okay, well, from this point here, 4.5 distance, from this point 3.1, from this point is 2.4, from this point is 2.4. So you can do a ranking of all the points that it's closest to. And so essentially we're finding the nearest neighbors. That's where the idea comes from. And the K on the nearest neighbors is we determine the number of points that we should consider in determining how close we are. And so let's say we say K equals 2. Then we will say, okay, K equals 2, so I'm only going to consider the two closest points, which may be these two here, because these are not that close. Now it's easier if the 2 points that it's closest to are in the same group, but what if it's one is here and one is here? Well, to do that, maybe it needs to vote. It's kind of vote on the predicted class labels based on the classes of the K nearest neighbors. Here the labels were predicted based on K equals 3 nearest neighbors in this example here. So you got to do some averaging essentially to do that. So that's why it's actually good to use 3. So if you have, let's say, your new point is equal distance from the lime green to the green. It's 2 here and then 2 here. So, well, the model is not going to know which one to classify it on. I mean, you can just randomly assign to each, but if it's the same distance to one green and one yellow, then it doesn't know where to go. This is why it's actually good to use an odd number, because now we have another nearest neighbor to bring it to the calculation. Maybe in this case it might be this one here. And now, oh, I see that actually I'm closer to these two than on average. You got the average of these two, and then compared to this one, I'm closer to these two. So it would assign it to maybe the yellow in this case. So I think we kind of went over here. I had another example just in case we needed, but automated detection of wine. Let's say you have two variables to measure wine, routine and myricetine. So these are kind of like wine characteristics. The KNN model is trained with existing data, so the KNN is going to calculate how different the routine and the myserine are from all of the other points from each other, kind of like that. Calculates the distance. And then we're going to have a new wine that is this X amount of routine and Y amount of myserine. A new mystery wine is introduced, and now the model needs to determine if it is red or white. To do so, the KNN model calculates the distance between the new wine and all of the existing wines. So it checks how distant in terms of routine and myserine, in this case it is. And then we determine how many existing points wines the model should consider by assigning a value to K. Remember, we need that K. So if K is just, 2, it may only select these 2 here. And there's a more neat example here. This is the new thing that needs to be determined. If it's K's here, you would put a radius around it that only selects the 3 nearest. Now, if we have K equals 7, it may look at the 7 other ones, so it's going to include these other ones as well. So that's the idea of the K, and then calculating the distance from each other and the nearest neighbors. So one of the issues is how to choose K. There are no predefined statistical methods to find the most favorable value of K. But generally, choosing smaller values of K can be noisy and will have a higher influence on the result. If you just have, one, let's say K equals 1, it's just looking at one nearest neighbor, so it's not really good. Generally, larger values of K will have lower variance but increased bias. Lower variance but increased bias. Also, it's computationally expensive, so often we don't want a large number of Ks, because then you got to calculate all of them. Now, let's look at this lower variance and increased bias. Lower variance meaning that the variation on the results that you get from the different predictions is going to be lower, because we're considering a lot of the data in our calculations. But it could increase bias, meaning that if we're using a lot of data, the data can be putting our item consistently in the wrong category. A cross-validation means we divide the data set in different chunks and train and test them several times to assess the best value. Remember how we have both a train and data and test set? So we can kind of switch these up a little bit, randomize different train and test sets, and this is part of the cross-validation to make sure that we train a better model. We can also derive a plot between error rate and K denoting values in a defined range, and then choose the K as having a minimum error rate, and we can do this in different ways, and I'll show you one way to do it as well in our Jupyter Notebook. Generally, a good value of K is the square root of the n, where n stands for the number of samples in your training data set. Try and keep the value of K odd in order to avoid confusion between two classes of data that may have similar values. So these are some of the notes there. There's some good references as well for you to look farther deep into this. Now here's on applying KNN in Python. It's fairly simple to begin with. Just the basics are simple. So first we import the KNeighbors classifier from the SciKitLearn data package. And then what we have to do is we initialize the model. We initialize the model, KNeighbors classifier, with our desired K. The K is usually applied at the end when we predict, but it's important to know it when the train as well. And that's it. We just initiate it and put it into a variable that we name it KNN. And then after we initiate it, we used our train data sets and our Y train data set. This is usually just a single array. And this is the whole data frame of the different predictors we created in previous steps. And then we use the fit method for that of our KNN object. And that's pretty much it. Once you train it, and it's done. Now after you train the model, you have a built model, and we can use the test set to test the model, the accuracy. And you can also just use the predict function to predict any values, the test set or just a particular set of values. So our data was organized in this order, so you got to be careful too about this. When you do this, you got to have follow this order. So our order was mass, width, and height. We had three columns, three features. So you can actually put any value of a new object. Maybe you get a new object with mass 20, with 4.3 and height 5.5 in, of course, these scales that we're using here. And then it will give you a fruit prediction for that. And here, this lookup fruit name is just that at some point we switch the label with the name. So here is just connecting the label with the name. And once you apply this value, you'd get, a result. Maybe, well, this looks like the model predicts this is a mandarin, given the information that you gave us. But the idea is that we can use this function here to make the prediction from the built model. And I also give you some code to plot the different accuracy scores using different values for K. So here's just a loop that trains and then tests data sets based on different K values. Just a loop, it's just doing the same thing that I just went over multiple times with K at different values. And here, note that we're both fitting the data set and we're also getting the score, because you can get a score with the test set that we separated, that we did not use in the training of the model. And then the score function here is going to give us an accuracy score, which I will mostly talk about in the next lecture. But essentially, this is the percentage, is the accuracy. So percentage of number of classifications that it did correctly. So this loop creates a number of different models with different K's values, and then also creates this list of the different scores of the different models with the different K. And then it just plots out at the end the results. So in this case over here, we see that this model with a low K, this K over here, low K, had accuracy 0.6, which means 60% of data correctly predicted. And then as we increase the K, the accuracy keeps going down lower. Now, this is not often the case, depends on the data. This is not often the case though. Usually with K goes up, the accuracy goes up with a certain limit. But in this case, actually, ideal K would be pretty low. I don't even know what this is, if this is 1 or 3 or so. But 5 already kind of reduce it. So this with K could be that we actually, the accuracy seems correct, but when we test in multiple different data, because K is very small, only one, we're only considering one nearest neighbor. So this could give either high variance or high bias on our results, which we do not want. So that's the basic idea of the K nearest neighbors algorithm. And next, we're going to be talking about these accuracy measures and other measures on how to evaluate this in other models.